A warm welcome to all of you. I present this mainly for second semester chemistry students of our college during the critical situation of COVID-19 pandemic. This presentation is about practical instruction. In this cycle 1, I have to discuss 5 experiments which are in the syllabus of our university, Bharadasan University. This slide shows Physical Chemistry 1 syllabus of Physical Chemistry Practical 1 syllabus of our university. I have discussed 5 experiments. What are the 5 experiments? One experiment, kinetics acid hydrolysis of ester, comparison of strengths of acids. And another experiment, determination of molecular weight of substance by transient temperature method. Another experiment, determination of molecular weight of substances by Rost method. And another experiment, study of phase diagram of two components forming a simple eutectic. And the fifth one is distribution law, study of iodide-iodine equilibrium. This slide shows a request to viewers. First experiment, determination of molecular weight by Rost macro method. The method is macro method. Aim of the experiment to determine the molar depression constant Kf value of the given solvent using the solute of known molecular weight and molecular weight of the given unknown solute by using the same solvent. That is, this experiment, 3 substances are given to the students and one substance, that is solvent, another substance is known solute, another one is unknown solute. Known solute means that is the molecular weight of that solute is known, that is given, that is known solute. Using Rost method, first determination is molar depression constant of the given solvent, and second one is molecular weight of given unknown solute. Now principle of this experiment, that is principle is it depends upon it is based on colligative properties. Now one of the colligative property, that is depression freezing point, that is freezing point of pure solvent is depressed by the addition of solid particles, and depression freezing point, that is delta Tf, that is directly proportional to molality. So molality means number of moles of solute present in 1000 grams of solvent, that is W2 into 1000 divided by M2 into W1. W2, that is weight of solute, M2 molecular weight of solute, and W1, that is weight of solvent. So the molality formula, that is W2 into 1000 divided by M2 into W1, that is number of moles of solute present in 1000 grams of solvent, that is molality. Okay. Now the delta T of depression freezing point is directly proportional to molality, that is equal to Kf into molality, where Kf, that is molar depression constant of the solvent, that is Kf. So by this experiment, by using known solute and the experiment determination of freezing point of pure solvent and solution of solvent and known solute, that is delta Tf is equal to T1 minus T2, where T1 is the freezing point of pure solvent and T2, that is the freezing point of solvent plus known solute. And from this delta Tf, that is depression freezing point, and knowing the molecular weight of known solute, we can simply calculate the value of Kf by using the formula delta Tf is equal to Kf W2 into 1000 divided by M2 into W1. After determination of Kf of the solvent, we can calculate the molecular weight of unknown solute by determination of delta Tf of delta Tf value, that is T1 minus T3, where T1 is the freezing point of pure solvent and T3, that is the freezing point of solution containing solvent plus unknown solute, solvent and unknown solute. So by knowing experimental determination of delta Tf and the value of Kf, we can simply calculate the value of molecular weight of unknown solute. That is the principle behind this experiment. Now materials required for the experiment, that is TT apparatus, sensitivity thermometer, beaker, solvent, and the known solute B, unknown solute C. Before starting the experiment, students check the materials required for the experiment. Now, procedure of this experiment: 5 gram of the given solvent A, is taken in a TT apparatus inner jacket, and the inner jacket is heated slowly in a water bath without outer jacket, and the solvent is melted, and noted the temperature exactly and melting of the solid. That is, the temperature at which the solid is changed to its liquid state, that temperature is exactly determined. Then it is taken out from the water bath and fitted with an outer jacket and allowed to cool with constant stirring, and the temperature at which solid appears, that temperature is exactly noted. The average of these two is the freezing point of the solvent, and the freezing point and melting point both are practically same, but some small deviation may occur. So the average of these two is the freezing point of the solvent. Now to this solvent, 5 gram solvent, 0.5 gram of solute of known molecular weight is added. For this mixture, the melting and solidification temperature are noted as before. From the depression of freezing point, Kf value is calculated using the known molecular weight of the solute. From the formula, Kf is equal to delta Tf into M2 into W1 divided by W2 into 1000. Now the same experiment is repeated by washing the inner jacket and by taking known amount of solvent, that is 5 gram, and solute known amount 0.5 gram of unknown solute, and the depression of freezing point of this mixture is noted as before, and the molecular weight of unknown solute can be calculated using the formula M2 is equal to Kf into W2 into 1000 divided by delta Tf into W1. Here W1 weight of solvent, that is 5, W2 weight of solute 0.5 gram. So using this formula we can simply calculate molecular weight of unknown solute. This slide shows observation and calculation and tabular column, and the freezing point of pure solvent on heating and cooling, and the average is recorded. And similarly for the mixture means weight of solvent plus uh, known weight of solute 0.5 gram of known solute, and also for mixture containing solvent and unknown solute. All these freezing point of all these substances are recorded in the tabular column, and here T1 is the freezing point of pure solvent, and T2 is the freezing point of solvent plus known solute, and T3, that is the freezing point of solvent plus unknown solute. So determination of Kf formula is given, and here delta Tf is equal to T1 minus T2, and determination of molecular weight, the formula is given, and delta Tf is equal to T1 minus T3, and the result of the experiment, that is molar depression constant of the given solvent, that is one result. Another result is molecular weight of given unknown solute. Suppose one more unknown solute also given during the practical examination. The next experiment is phase diagram experiment. Aim of the experiment to construct a phase diagram for a binary mixture and to determine the eutectic temperature and the corresponding composition. Now phase diagram means that is a diagram which shows phase changes during temperature changes. Now principle of this experiment, that is when a binary mixture means which contains two components, is cooled, a solid separates out, which depends upon the composition and nature of the substance. And here the eutectic mixture means that is a mixture of two components which has a particular composition which has the lowest melting point of on addition of the two components, that is eutectic mixture, and corresponding temperature is called as eutectic temperature. That is eutectic mixture means that is a mixture of two components which has lowest melting point. That composition is called as eutectic composition. Now materials required for the experiment, that is TT apparatus set, sensitivity thermometer, beaker, component A and component B. Now procedure of the experiment. Here the substance A and B are given, two substances. From substance A, 3 gram packet 1 packet and 0.3 gram packets 5 packets are weighed. Similarly in the case of the substance B is also weighed in this way, 3 gram and 0.3 gram in 5 packets. Now first 3 gram of given component A is taken in a TT apparatus inner jacket, and the tube is heated in a water bath without water jacket, and the component A is melted and noted the temperature at melting of the solid exactly. Then it is taken out and fitted with an outer jacket and is allowed to cool with constant stirring, and the temperature at which solid appears is noted. Practically, the melting and freezing both are same, and now the average of these two is the freezing point of component A. To this component, pure component A, 0.3 gram of component B is added, and for this mixture, the melting and the solidification temperature are noted as before. Similarly, freezing points of mixtures are noted by 4 more addition at the installment of 0.3 gram of component B. All the freezing points are tabulated in the table 1. Now the TT apparatus is washed well with water and drained, and the same procedure is repeated by taking 3 gram of the given component B, and the freezing point is noted, and the freezing point of mixtures are noted by 5 more addition at the installment of 0.3 gram of component A. All the freezing points are tabled in the table 2. Now freezing points are plotted against percentage composition of A and B in the same graph using the table 1 and 2. Two straight lines are obtained with the maximum points on the line. The temperature corresponding to a point at which two lines meets is eutectic temperature, and corresponding composition is eutectic composition, and the model graph is given in this slide. This slide shows tabular columns and percentage composition of a calculation and the result of the experiment, that is eutectic temperature of binary mixture and also the eutectic composition. The next experiment is transient temperature experiment. Aim of the experiment to determine the transient temperature of the given salt hydrate and to determine molar transient temperature constant KTR value of the given salt hydrate using the solute of known molecular weight, and to determine molecular weight of the given unknown solute by using the same salt hydrate. Here, 3 substances are given, and one substance is salt hydrate, and the remaining 2 are substances which are water soluble. And here salt hydrate means that is the salt which contains water molecule in the molecular formula, that is salt hydrate. And the transient temperature means that is the temperature at which the salt hydrate is changed to is anhydrous salt. It's anhydrous salt. That is, at the transient temperature, the salt hydrate and anhydrous salt both are in equilibrium, and that temperature, the process occurs at a particular temperature. That temperature is called as transition temperature. Next principle of this experiment. Here the transition temperature of the salt hydrate is depressed by the addition of solid particles, and depression transition temperature, that is directly proportional to molality, and that is equal to delta Tr, that is equal to Ktr W2 into 1000 divided by M2 into W1, and by knowing M2 value and by experimental determination of delta Tr, we can simply calculate the value of Ktr first, and from the value of Ktr and by experimental determination of delta Tr using solvent and unknown solute, and from these values M2 is calculated from this formula. M2 is equal to Ktr into W2 into 1000 divided by delta Tr into W1. Here first by using known solvent, that is Tt of pure solvent, that is T, let it be T1, and freezing point of not freezing point, transient temperature of salt hydrate plus known solute, that is T2, and transient temperature of salt hydrate plus unknown solute, that is T3. So T1 minus T2, that delta T, that value, from the value first Ktr value is calculated, and delta Tr, T1 minus T3, from this value we can simply calculate molecular weight of unknown solute, and here W2 weight of solute, W1 weight of solvent. Materials required for the experiment: one is salt hydrate, another one is solute, known solute, unknown solute, and the sensitive thermometer, TT apparatus, beaker, and timer. Here the procedure of the experiment: 5 gram of salt hydrate is taken in a TT inner tube, inner jacket. The inner jacket is heated slowly in a water bath, raising the temperature with a continuous stirring. The temperature at every 30 seconds is recorded. The temperature of the salt will rise slowly and in a regular manner until the temperature becomes practically constant at transition point and the salt becomes partially liquid. Afterwards, the inner jacket is removed from the water bath and allowed to cool using outer jacket, and the temperature readings are taken at every 30 seconds until temperature becomes constant for a short period of time due to the liberation of heat in the transition of anhydrous salt into hydrate form. And here the constant temperature for short period of time is transition temperature. Now the values are tabled in the table 1. The same procedure is repeated for 5 grams of salt hydrate, the 0.5 gram of known solute, and the values are tabled in the table 2, and also for 5 grams of salt hydrate, the 0.5 gram of unknown solute, and the values are tabulated in the table 3. So on plotting the graph of temperature against time in seconds, heating and cooling curves are obtained. From this curve, the transition temperature is determined corresponding to the line which is parallel to time axis. That temperature is called as transition temperature. Now this slide shows model graph and tabular column, and here are the formula to calculate KTR and the formula to calculate molecular weight of unknown solute, and the result of the experiment. One is transition temperature of given salt hydrate, another is molar transition temperature constant value of the given salt hydrate, and third one is molecular weight of given unknown solute. Fourth experiment, partition coefficient and equilibrium constant. Aim of the experiment to determine the partition coefficient for the distribution of iodine between organic layer, and the layer is our solvent is benzene, and water, aqueous solvent. And another aim to find out the equilibrium constant of the reaction Ki plus I2 reversible arrow Ki3. And third one to find out the strength of unknown K using equilibrium constant. Here the iodine is solute which distributes in two solvents. One is organic solvent, another one is water solvent, and the partition coefficient, aim of the experiment to determine partition coefficient for the distribution of iodine between organic solvent and water solvent. And another aim to find out the equilibrium constant of the reaction Ki plus I2 reversible or Ki3. It is a reversible reaction, equilibrium reaction. And third one to find out the strength of unknown Ki, the given Ki solution using equilibrium constant. By knowing the equilibrium constant and to find out the strength of unknown Ki. The principle of this experiment, that is Nernst distribution law. According to Nernst distribution law, when a solute is added to a system of two immiscible solvents, the solute will be distributed itself the two layers of the solvent in a constant ratio at constant temperature, provided if any dissociation of solute in solvent, any dissociation or association of solute in solvent. That is, here the solute is iodine, and the iodine distributes between the two layers, and here the solvents, two solvents, one is benzene, another one is water, and here the iodine distributes the two layers with a constant ratio at constant temperature. That ratio, that is called as partition coefficient. The ratio is known as partition coefficient. And when Ki solution is added to a system containing iodine, then there is a possibility of attaining the following equilibrium, that is Ki plus I2 reversible arrow Ki3. So at equilibrium, the equilibrium constant, that is given by concentration of Ki3 divided by concentration of Ki and concentration of I2. By determining all these concentrations at equilibrium, we can simply calculate equilibrium constant. And if the strength of Ki is not known, that can be calculated using the above formula by knowing K equilibrium constant. Now the materials required for this experiment, that is, one is iodine in benzene, and benzene pure solvent, and 0.1 N thio, 0.1 N Ki solution, 10% Ki solution, and starch indicator, and potassium dichromate salt, and burette 50 ml, pipette 5 ml, 10 ml, and conical flask, and stoppered bottles, that is numbered bottles from 1 to 6, that is 6 bottles. Next procedure, preparation of reaction mixture in various bottles, bottle 1 to 6. In bottle number 1, 20 ml of iodine benzene and 100 ml water. And in bottle number 2, 15 ml of iodine benzene, 5 ml of benzene and 100 ml of water. And in bottle number 3, 20 ml of iodine benzene, 100 ml of 0.1 molar Ki solution. And in bottle number 4, 15 ml of iodine benzene, 5 ml of benzene and 100 ml of 0.1 molar Ka solution. And in bottle number 5, 20 ml of iodine benzene and 100 ml of given unknown Ka solution, that is one solution. And in bottle number 6, 15 ml of iodine benzene, 5 ml of benzene and 100 ml of unknown K solution, another solution, all are taken in various bottles. Anyhow, the bottle's total volume is 120 ml and the aqueous layer is 100 ml, exact 100 ml, and organic solution is 20 ml, exactly 20 ml. So total volume is 120 ml. So next, standardization of thio, about 1 gram of potassium dichromate is weighed accurately and transferred into 200 ml SMF and made up to 200 ml with water, with the distilled water. And this strength of this dichromate solution is about 0.1 normality. Exact strength is calculated. 20 ml of this dichromate solution is pipetted out into a clean conical flask, and to this 1 teaspoon of 2N sulfuric acid, dilute sulfuric acid, followed by 10 ml of 10% K are added, and this solution is titrated against sodium thiosulfate using starch as indicator, 1 ml of starch. And the endpoint is the disappearance of dark blue color. This titration is repeated for concordant value. From the titer value, the exact strength of thio is calculated. From this, 10 times diluted sodium thiosulfate is also prepared by pipetting 20 ml of the solution to 20 ml of about 0.1 normality. Sodium thiosulfate solution is pipetted 2 into 200 ml SMF, and the solution is made up to 200 ml. That solution has the strength 0.01 normality approximately. That strength is exactly calculated. Now, determination of iodine organic and aqueous layer. The 6 reaction mixture bottles are stopped and shaken in a mechanical shaker for at least about 45 minutes. After attaining equilibrium, organic and aqueous layers are separated using separating funnel, and 20 ml of the aqueous layer from bottle 1 is pipetted out in a clean conical flask, and about 10 ml of 10% Ka solution followed by 1 ml of starch are added, and the solution is titrated against 0.01 N thio taken in the burette. The endpoint is the disappearance of dark blue color, and the titration is repeated for concordant value. Then afterwards, 5 ml of organic layer, benzene layer is pipetted out in a clean conical flask, and about 10 ml of 10% Ka solution followed by 1 ml of starch are added, and the solution is titrated against 0.1 normality thio taken in the burette till the end point. Here also the end point is the disappearance of dark blue color, and the titration is repeated for concordant value, and the same procedure is followed for the bottles 2 to bottle number 6, 2 to 6, and the titer values are recorded in the table 3. And from the weight of dichromate, normality of dichromate is calculated using the formula weight of dichromate into 5 divided by 49. That is the normality of dichromate. The table 1 shows the various concentration of iodine benzene on water in various bottles, bottle number 1 to 6, and table 2 shows the titer value, the titration between standard dichromate versus thio, and from this titer value, the strength of thio is calculated using the formula, that is 20 ml of standard dichromate solution of dash normality is equal to dash ml of thio. Therefore, strength of thio is equal to 20 into strength of dichromate divided by titer value, thio value. From this, the exact strength of thio is calculated. Now, table 3 shows the titer value on titration of 5 ml of organic layer with 0.1 N thio, and 20 ml of aqueous layer with 0.01 N thio. Here the titer values are given in this table. Actually, here bottle 1 and 2, using these two bottles we can determine partition coefficient, and using bottle number 3 and 4 we can determine the equilibrium constant, and from the equilibrium constant the strength of unknown solution in bottle number 5 and 6 are determined. From bottle number 1 and 2, partition question can be determined, and the values, titer values are indicated as V1 and V2. V1 and V2 for bottle 1, V1 and V2, and for bottle 2 also V1 and V2, because these two bottles are used to determine partition coefficient. So now KD, that is the concentration of iodine in benzene layer divided by concentration of iodine in water aqueous layer. Now concentration of iodine in benzene, that is V1 into 0.11 divided by 5. Similarly, concentration of iodine in water, that is given by V2 into 0.01 divided by 20. So on substituting these values in this equation, we can get a equation, that is V1 into 10 into 4 divided by V2. So using this and by substituting V1 and V2, we can calculate partition coefficient for bottle number 1 and for bottle number 2. So average of partition coefficient is calculated by adding these two followed by divided by 2. So from bottle number 3 and 4, the equilibrium constant for the reaction Ka plus I2 reversible or Ka3, that can the equilibrium constant is calculated for this reaction, equilibrium reaction. Now K equilibrium constant, that is given by concentration of Ka3 at equilibrium divided by concentration of Ki at equilibrium and the concentration of iodine at equilibrium. Now concentration of iodine organic layer, that is given by the formula, and volume of thio into normality of thio divided by 5, and to change the normality into moles per liter, it is divided by 2. So concentration of iodine in organic layer, here volume of thio, here the for bottle 3 and 4 volume titer values are indicated as V3 and V4. For organic layer V3, and for aqueous layer the value is V4, and the volume of thio in normality of thio divided by 5 into 2. The answer is in moles per liter. Similarly, in the case of concentration of iodine in aqueous layer, that is determined by volume of thio, that is V4 into normality of thio divided by 20 into 2. The 2 for to change the normality into moles per liter. So now this concentration of iodine organic layer, let it be C1 moles per liter, and concentration of iodine aqueous layer, let it be C2 moles per liter. Now concentration of free iodine in aqueous layer, that is iodine free after attaining equilibrium, that is given by C1 divided by Kd, and by substituting value of C1 and Kd, we can calculate concentration of iodine which is in free, that is concentration of iodine at equilibrium. Let this equation be 2. So the concentration of iodine aqueous layer, that is C2, that is the total iodine in aqueous layer, that is the sum of concentration of Ki3 and free iodine. So from concentration of free iodine and from the value of C2, concentration of Ki3 is calculated by C2 minus concentration of iodine which is free. There is C2 minus iodine free, that is C2 minus equation 2 value, that is concentration of Ki3 at equilibrium. Let this equation be 3. Now initial concentration of Ki, that is 0.1 molar. Now K unreacted, that is the K at equilibrium, that is given by 0.1 minus equation 3 value. So let this equation be 4. By substituting equations 2, 3 and 4 in the equilibrium constant equation, we can simply calculate equilibrium constant, that is K equilibrium is equal to concentration of Ki3 at equilibrium divided by concentration of Ki at equilibrium and concentration of iodine at equilibrium, that is iodine free. So by using bottle 3 and for bottle 4 equilibrium constants, these values are calculated, and the average of these two is calculated. Using that value equilibrium constant, we can determine concentration of unknown Ki in the bottle number 5 and 6. So after determining equilibrium constant, next step is to find out the concentration of unknown Ki solution in bottle number 5 and 6. Here the titer values are indicated by the symbols V5 and V6. That is V5 for titer value for organic layer and V6 titer value for aqueous layer. And here the organic layer is titrated against about 0.1 n thio. So the normality of thio, the exact value is about 0.1 n, that is substituted in the determination of concentration of iodine in organic layer, benzene layer. In the case of concentration of iodine aqueous layer, the normality of thio is 0.01 n, the exact value is substituted. So concentration of iodine benzene layer, that is volume of thio, that is V5, in the normality of thio about 0.1 n divided by 5 into 2, that let it be C1 moles per liter. And concentration of iodine aqueous layer, that is volume of thio V6, and the normality of thio, that is about 0.01 n divided by 20 into 2. The answer is C2 moles per liter. So C1 moles per liter, that is the concentration of iodine in benzene layer, and C2 moles per liter, that is concentration of iodine in aqueous layer. Now concentration of free iodine in aqueous layer, that is iodine free, that is concentration of iodine benzene layer divided by Kd, that is C1 by Kd, that is concentration of iodine free. Let this equation be 5. And concentration of Ki3 at equilibrium, that is total iodine concentration in aqueous layer minus iodine free, that is C2 minus iodine free. C2 minus the value of equation 5, and substituting C2 and equation 5 value, we can simply calculate the value of Ki3 concentration at equilibrium, let this equation be 6. Now initial concentration of Ki, that is let it be C3, that is unknown, and equilibrium concentration of Ki, that is concentration of iodide at equilibrium, that is C3 minus concentration of Ki3 at equilibrium. Now that is given by C3 minus equation 6 value. Let this equation be 7. So and by substituting value equations 5, 6 and 7 which has C3 value, and by substituting value of equilibrium constant, we can simply calculate the value of C3, that is the initial concentration of iodide, that is the concentration of given Ki solutions in bottle number 5, from bottle number 5 and also bottle number 6. And here these values are all these values are reported, and the result of this experiment, one is partition coefficient for distribution of iodine between benzene and water, that is one. Another one is equilibrium constant of reaction of Ki3 formation, that is another result. And another result, that is strength of given Ki solutions 1 and 2, given solution 1 and given solution 2. Next experiment, fifth experiment, is kinetics of acid hydrolysis of ester. The aim of the experiment, that is to determine rate constant for the hydrolysis of given ester by given acid A and acid B at room temperature and the ratio of acid strength A and B. That is, students are given two acids separately, that is acid A and acid B. And by studying the kinetics of hydrolysis of ester by acid A first and followed by another acid B, one can determine the ratio of acid strength A and B. That is the aim of the experiment. Next, principle behind the experiment, that is esters are hydrolyzed by dilute mineral acid solution. That is, ester is hydrolyzed to acid and alcohol, and the reaction is pseudo unimolecular reaction when water is present in excess. So in the case, if water is in excess, then the rate of the reaction is directly proportional to only ester. Therefore, the reaction is pseudo unimolecular reaction, and the order of the reaction is 1. And here two acids are given, and the rate constant of the hydrolyzed ester by acid, that is determined first, and followed by rate constant of hydrolyzed ester by acid B, that is determined, and the ratio of these to rate constant, that is the ratio of strength of acid A and B. And materials required for this experiment, that is first one ester, either methyl acetate or ethyl acetate, ester, and another one 0.1 n sodium hydroxide, from indicator, ice, cold water, ice and cold water, burette 50 ml, pipette 5 ml, 10 ml, conical flask, reagent bottles, acid A and acid B, two bottles. Now next procedure of this experiment, acid A is placed in a thermostat or water trough which has water, and this is for attaining the acid to room temperature. This bottle is placed at least 5 minutes, for about 5 minutes, and after 5 minutes 10 ml of ester is added in the reaction bottle. Ester is added to the reaction bottle and shaken well. When volume of the pipette is about half of the volume, a stopwatch is started and the time is zero time, and immediately after draining the ester to the bottle, the reaction mixture bottle is shaken gently, and immediately 5 ml of reaction mixture is taken in a conical flask which contains some piece of water, some piece of ice and water, and from the indicator, and the solution is titrated against 0.1 sodium hydroxide, which is already standardized and which is taken in the burette. And now the titer value is noted as V0, and the endpoint is appearance of pink color is the endpoint, and the titer value is noted as V0. And after 10 minutes, the reaction mixture, from the reaction mixture, the same volume, that is 5 ml of reaction mixture, is pipetted out in a conical flask which contains ice water, and from the indicator and titrate against the same sodium hydroxide solution which is taken in the burette, and this titer value is noted as Vt. And similarly after 10 minutes, that is 20 minutes, 30 minutes, 40 minutes, 50 minutes, 60 minutes, this same procedure is followed to determine Vt value at various time, 20 minutes, 30 minutes, 40 minutes, 50 minutes, 60 minutes. So after taking 6 readings, Vt value, the reaction mixture is heated in a water bath in low flame for about 30 minutes, and after heating 30 minutes, the reaction mixture is cooled, and from that 5 ml of reaction mixture is titrated against sodium hydroxide using frothing indicator. This value is noted as V infinity. So from the value V0, Vt, V infinity value, the rate constant value is calculated at various time, 10 minutes, at 20 minutes, 30 minutes, 40 minutes, and 50 and 60 minutes. So we have 6 readings, and all these readings are tabled in the table 1, and the rate constant of the readings, average of rate constant, is calculated by adding all these values divided by 6. That is the rate constant of hydrolysis of ester by acid A, that is Ka. Here A for acid A for acid A. So the same procedure is followed for acid B also, and calculate the rate constant Kb. B means acid B, and the same formula, Kb is equal to 2.3 by T log V infinity minus V0 divided by V infinity minus Vt. From the value of Ka and Kb, the ratio is calculated. That ratio is the ratio of acid strength, that is by experimental method. The same acid strength ratio value is also calculated from the graph. So for that, log V infinity minus Vt is plotted against time. We get a straight line. From the straight line, slope can be determined, and from the slope, K is calculated using the formula. K is equal to 2.303 into slope, and this is done for both acids, acid A and B, and from that we can calculate the ratio of rate constant Ka by Kb by graphically, and that is the ratio of acid strength by graphical method. So we can report as ratio of assistance by experimental method and also by graphical method. So that is next slide shows all these table and the result of the experiment. This slide shows tabular column and result of the experiment. That is ratio of assistance. One Ka by Kb by experimental method. Another one is Ka by Kb by graphical method. And the unit of rate constant here, that is per minute, minute power minus 1. This slide shows university practical questions of these experiments. For experiments 1 to 5, these are the questions. These are the questions asked in the university practical examination. With this, I want to conclude my lecture on practical instruction in the non-electrical experiment in under cycle 1. I think it is very useful for PG students of our Bharatdasan University. I wish all the students all success. I express my sincere thanks to all viewers, and also I want to get positive and negative comments from viewers. That makes me the future lecture in a better way. Once again, I thank one and all. Thank you.